closed box has fixed area A and a square base with side x. A from the formula of the volume V of the box is a function of x. What's the domain of V? B, graph the volume V as a function of x, and C, find the maximum value of V. So here, if we draw that closed box, notice the base gonna be x with side x, and then the height gonna be h. Notice that the base and the bottom, the top, they are the same thing. So again, this is the base, the side gonna be x, and then x. It's just basically a square. Now A, we want to have the function v of x and its domain. So here the volume is rectangle. So what does that mean? The volume gonna be height or length multiplied by width multiplied by height. Now volume gonna be equal to the length is x and the width is also x and the height h. Therefore the volume gonna be x squared multiplied by h. Now we want A asks us to write the volume as in term of x. So we want to write h in term of x. So let's move to the surface area. Note in here, if we have an exploit of the rectangle here from this closed box, what we're gonna have, we have 1, 2, 3, 4, 5, and 6 areas. So we have area of 1, 2, 3, and 4. These gonna be the same areas. So these are 4 areas, and then by this shape, and this shape gonna x, and this is the height h. Now we have the top and the bottom, so that is 2 areas, so that gonna be 2 multiplied by that shape. And remember, this is a square. Now A can be written as 4xh plus 2x squared. Now we want to solve for h. Therefore, I'm gonna move 2x squared to the other side. And then I'm gonna divide on 4x, which is what is in front of h. Now the volume gonna be x squared. I'm gonna substitute the value of h, which is a minus 2x squared over 4x. Now I can simplify, so again I have x and then multiply by a minus 2x squared over 4. Now I'm gonna distribute the x inside the parentheses, so we're gonna have ax minus 2x cubed over 4. And then I'm gonna make them 2 fractions, so ax over 4 minus 2 over 4x to the cube. And then I'm gonna simplify this term, so the second gonna be, the fraction gonna be half x cubed. This is the volume in term of x. Now we want to find the interval of x. So notice here, we have the surface area A. Here, the area of the bottom plus the area of the top it should be less than or equal to the surface area of the whole shape. So remember, the area of the top and area of the bottom, they are equal, they are squared. So we're gonna have 2x squared less than or equal to a. Again, I'm gonna divide on 2, and then I'm gonna take the square root of 2. Notice x is just a length. So I'm taking the square root, I'm gonna just take the positive value. Therefore here, x gonna be between 0 and positive square root of a over 2. Now for part B, graph the function v in term of x. So remember here, v of x gonna be a over 4x minus half x cubed. Now a, it's a surface area, and area is just positive, and here a is just a positive constant. And notice here, when we graph this function, the volume is always gonna be positive. You will not graph the negative side, it's only the positive side, and gonna be look like this. We can graph it using graphing calculator. Here we want to determine where is the graph intercept with the x-axis. That is when v equal to 0. So the first scenario we have that when x equal to 0, that is here the first term. Now the second gonna be when a over 4 minus half x squared equal to 0. Here I'm gonna solve for x, so I'm gonna move the first term to the other side, and then I'm gonna multiply by 2 both sides. Now I'm gonna take the square root. Remember, when we take the square root, we have positive and negative. But again, x is just a length, and the length should be positive. So I'm just taking the positive value. Therefore, x gonna be square root of a over 2. I already noted that on the graph. Now C, find the maximum value of v. Since here we want to find the maximum value, this means we want to find a global maximum. So to find a global maximum, what I'm gonna do, first I'm gonna copy the function v of x, and then I'm gonna find a critical point of that function, and then evaluate our critical point and endpoints, and then decide what's the global maximum for the function. So again, first step is where our critical point. And remember, our interval, it's gonna be between x of 0 to square root of a over 2. Now critical point is where the first derivative is 0 or undefined. So what I'm gonna do now, I'm gonna take the first derivative of v of x, notice this function is defined for all values of x, including our interval, which is going from 0 to the square root of a over 2. Now where is the first derivative is 0? Here I'm gonna solve for x, so I'm gonna move the first term to the other side, and then I'm gonna multiply by the fraction 2 over 3. Now I'm gonna simplify in here. That's gonna be a over 6, since 2 multiplied by 3 is 6, Then I'm gonna take the square root of x, and then that's gonna be square root of a over 6. Remember, x is just a length, therefore I'm just taking the positive value. Now we have x equal to the square root of a over 6. This is included in our interval from 0 to the square root of a over 2. Therefore, it's considered to be a critical point for our function. Now, step 2, I'm going to evaluate our critical points and our endpoint 0 and square root of a over 2 and the function v of x. And then I want to see what gives us the maximum volume. So here, this is the function v of x. I want to evaluate the function at our critical point, square root of a over 6. So first, I'm going to simplify the function. I'm going to factor x over 2. Now I'm ready to evaluate the function at square root of a over 6. And remember, x squared here gonna be square root of a over 6 squared, which is gonna be a over 6. Now I'm gonna take these two fractions. I'm trying to simplify these. So the first fraction, I'm gonna multiply it by 3. So gonna be 3a over 6 and then minus a over 6. Now I can subtract these. I went up with 2a over 6. Now I'll plug that value back into our function. Now notice that the 2 on the top can be simplified with the 2 on the bottom. We'll left off with square root of a over 6, and then I'm gonna transfer the square root to the power of half. Now notice the second term gonna be the power of 1. So now we have the same term, so I'm gonna add the powers. That is the value at x equal to square root of a over 6. Now the volume at x equal to 0 is just 0. And the volume at x equal to square root of a over 2 is also 0. We can see that from the graph from part B. Now we can notice that at x equal to square root of a over 6, we have a maximum value. Therefore, we have a maximum volume at x equal to square root of a over 6, and the volume value gonna be a over 6 to the power 3 over 2.